that was very interesting story. So I am very happy that you mentioned that our effort is rewarding. Hi. Today, I would like to start by thanking organizers for giving me the opportunity to talk to you about our story, and also for great job for preparing this symposium. I am from Tohoku University. Let me share. It came. Sorry, this is summary. Can you see my slide? No?
No.
Oh, how should I share? Okay. 画面共有。
That's better.
Yeah?
That's
Now,
best.
yeah. I'm
Good.
very sorry. I lost how to get into this conference, and I forgot to press X, so I could not get that. So I am sorry to lose some minutes, but I would like to talk to you today, X-ray diffraction study of nano-confined liquid. First, I can introduce you my colleagues. This is a collaboration of Professor Yagi's group of Spring 8. And these two people are working hard on the project. Masashi Mizukami, my colleague, and Yagi's colleague of Noboru Ota. They are the key persons for this work. And today I would like to introduce you briefly background of our work about surface forces measurement, confined liquid, XRD of confined liquid, and several topics we studied recently. I don't know how many of you are familiar with surface forces measurement. This is even developed before atomic force microscope, but now that the FM is much more familiar. We did measure interaction force using spring balance and obtain interaction force profiles, which is interaction potential profiles, so that the repulsion is plotted positive and attraction in negative and distances. So this is, we get so interaction profile. So this is considered best method for studying origin of interaction forces. But often that we do not know the origin so clearly. So I said that this is a good way to study sometimes interface, because we have, if interaction changes, that means something changed at the interface between the solid and liquid. And this is usually very difficult to study such interfaces very at molecular level. Also, we can take advantage of precise determination of distance by controlling surface separation. And also lateral force can be studied. And so these are something we take advantage for X-ray diffraction too. The conventional SFA surface force apparatus is shown in right-hand side. We have large surface. If you only know the FM, this is very different. We have a large spring of several centimeters, and this disc, which is usually glued, the substrate is usually glued on such disc, which has a diameter of 10 millimeters. So that, however, the distance resolution of surface gap is very precise of 0.1 nanometer. And the contact area is usually about 30 micrometer. So this is very large in XY plane, but in very precise in a height direction. So this is very unique setting. So I think we can bridge macro or mesoscale phenomena with none. Actually, there are not so many people doing this kind of study. But I feel this is very important because elucidation of interaction is essential for material science. Everybody will agree, but not so many methods compared to structure characterization. So this is generally very important and essential. And also characterization of solid-liquid interface is important in research of advanced materials. And complex matters, real matters can't be fully understood by a single molecular measurement, which is the most idealistic probably case for AFM. And the study of weak interaction is possible because of large surface area. And gradually, when we accumulate the knowledge about interaction, I started to feel combining these two information is actually we are making kind of accumulating knowledge about interaction, origin of interaction. However, conventional SFA surface force apparatus is not always enough for everything if we want to study materials. So we do sufficient instrumentation, like we constructed a twin pass SFA for opaque samples. This is only, actually, I think that only one SFA for opaque samples, practically. And we, for lateral force measurement, we developed resonance measurement. And which we, using this, we study intensively the property of confined liquid. Also, surface other than mica should be used. So we do make quite effort for preparing flat and smooth surface of various materials. And the evaluation of interaction forces is also very important. So we do complementary characterization, including X-ray diffraction. And models and simulation are important. Also, we recently developed a device for precise temperature control. So that let me shift to the confined liquid topics of confined liquid. The confined liquid, besides probably the what is, excuse me, the water structure, suddenly I forgot English name. The solvation of by water is was not so well known until this study was done in about now about 40 years ago. The Roger Fong and Jacobus HB found that when they confined OMCTS, very spherical molecule, in a narrow gap, there is a such oscillation in their forces, which corresponded to layered structure of molecules. And that is a very new finding at that time. And we continue such research using our device of resonance measurement, which is very sensitive to the change in property of confined liquid, because we use resonance signal of this top unit, which hanged by two springs. So we oscillated, and at the resonance frequency, the peak is very large, so that the property such as viscosity, when viscosity changes, the peak, resonance peak decrease. And the frequency and amplitude of such resonance peaks are very sensitive to other structuring and viscosity and friction and rigidity, such properties. So we use such techniques for studying confined liquid. And there are many interesting phenomena we could observe using such device. The right-hand side figure shows examples of such case. We confined liquid crystal. molecules between a gap and studied their viscosity using some models. Which this is the damping parameter correspond to the viscosity, and at the distances below 20 nanometer, viscosity started to increase like this. Then when we applied electric field, the orientation of liquid crystal changed to such a way, and viscosity, so that viscosity increases for such lateral motion. But at the distances below 10 nanometer, the two values started to coincide. That means that the electric field cannot change the orientation of liquid crystal at such narrow gap. So this is the first observation of such confinement effect. But naturally, then we wanted to know the structure of such cases. This is just a model to show that we can calculate viscous parameter or elasticity parameter using model. So then we became interested in an earlier attempt of using X-ray diffraction in SFA surface forces apparatus. The very early attempt of X-ray diffraction study using SFA was done by the group of Jacob Strachvili with his colleagues in Santa Barbara. I cannot read so well, but it's Isaac and Safin. They used capillary tubes, crossed capillary tubes, or the discs this is a disc same as identical as SFA, identical one for SFA as SFA, but with holes at the middle, and did the X-ray diffraction study and studied the shear-induced orientation of liquid crystal. But their case, they only can study distances about 400 nanometer and above. And if you remember my data, the confinement effect appears at distances smaller than 20 nanometer. So this is not enough sufficient for studying confined liquid. And we believe this is the first example of X-ray diffraction study from nano meter thickness liquid. We took very same setting as researchability group, but tried to really accumulate signals and improve the signals. But at that time, we do not know how to regulate different gaps in a small distance. So we did two cases at 2 micrometer and 2 nanometer. This is a very compressed hard wall thickness. But we could obtain the scattering spot like this. But this actually relaxed to no clear X-ray diffraction spot after 100 minutes. But anyway, this is the signal corresponding to the longer molecular length like this. And also at 2 micrometer, we have seen that also this short length corresponding to 0.43 nanometer, very small, small peak. But this peak is very clear, and this peak is very clear for 2 nanometer thickness field. Then we wanted to regulate better the distance. Now we do it with a feedback system, and most studied system we have done so far is ionic liquid. Ionic liquid has attractive property such as low vapor pressure, non-flammability, and stability, high ion conductivity. Therefore, they are expected to be used for many applications like electrolyte, solvent, and lubricant, etc. So that we wanted to know most of the application requires how the information about how they behave in a confined in small spaces. So we wanted to study them. If we studied two kinds of ionic liquid, which has the same cation and different anion, shown here. If we study normal force, there is a quite clear oscillation, which means layering. They have layered structure. But these two ionic liquid did not show so quite different behavior, although that with smaller combination shows shorter oscillation. However, if we look at this resonance peaks, this is a frequency and resonance amplitude. And when we change distance, peak changes from this frequency to this frequency. And so if this peak increases, that means we have larger viscous, we see that the viscosity of liquid is larger and friction is large. Traction between surface is large. But this means that there is low friction and lubrication properties very well here. And if we plot the viscosity, effective viscosity in terms of distance, although bulk viscosity is larger here, at confined situation below 10 nanometer, viscosity increase several orders of magnitude, but this shows a smaller viscosity increase, which is opposite to bulk values. So this kind of data shows that bulk measurement does not mean anything in a confined space. But why? Why this combination shows high viscosity and why this one is not? We did computer simulation with Alex Schulger's group, and the simulation shows very interesting behavior. In case of this larger cation, the cation and anion align alternatively. So the checkerboard like a organization with simulation indicated. And this BF4 minus case, that they same ions are organized in one layer and another ions, and this is alternate layer. So if you shear here, cation hit cation and anion hit anion, so this kind of shear mode is not favorable, so we see large friction. But this case, shear does not change structure so much so that we can move it smoothly. And we study X-ray diffraction from such systems using very thin silica sheet on mica. We could spatter such silica sheet on mica, and this is to avoid large background X-ray scattering. And the obtained signal for at 3 nanometer thickness film is shown here, which indicate such alternate alignment of ions. But in case of F4 minus, this peak up disappears. So this structure agreed with this such alternate layering of different ions. So we can show that such X-ray diffraction is very effective for characterizing confined liquid, and obtained results supports a different structure for different ionic liquid proposed by our simulation studies. So if the ions are aligned in such a way, the distance between ions are quite different depending on the cases, so that we do not see any clear diffraction peak. But this case, because of very clear organization, we see the peak. And I can briefly show you that how we could study shear effect. And in this case, we studied H2CB liquid crystal between mica or silica using similar setting. In case of mica, we have seen that such short the peaks little bit wide, 22 degrees spread, 22 degrees diffraction spot. But in this case, we have seen that rings, so which correspond to such more organized structure between mica, because we know that liquid crystal align along the crystal axis of mica. But in the case of amorphous silica, we do not see that such alignment along a certain axis, so we see that ring. If we share such systems at confined state, we only see that very small change in diffraction spot and angle change of by 3 degrees. But if we share at very large gap, and if we narrow the gap, we can observe shear effect of such. Because I would like to keep some time, a little bit quick at the end, but in summary, our studies show that X-ray SFA can be efficiently used for obtaining structure of nano-confined liquid. This can afford the useful information to understand their properties, which are quite different from the bulk. And I can mention that other groups now start using X-ray XFA, including Kekse's group. He used small angle X-ray, and Melgar's group of Max Planck for polymers in Mainz is using reflection mode. So I think now that we are quite able to study confined systems using X-ray SFA at molecular level. Thank you very much for your attention.
If you could connect, please.
Yes, hello, good morning. Let's see, I'm trying to share my screen. There we go. Does that look like what you expect?
Looks very good.
Okay, great. So thank you. And well, thanks the organizers for giving me a chance to present this work. I should say it's interesting to come after Professor Kurihara, because I made my PhD in surface forces, although that was 20 years ago. So it was an interesting flashback. Okay, so I will talk about something totally different now. So this is a project that I've been doing together with Rainer Dahint in Heidelberg, who is not attending this meeting. Yes, so I'm sure that a number of people in the audience can testify to the benefits and advantages of neutron reflectometry, not just at the solid liquid interface, which is what we will be dealing with, but despite all the greatness of reflectometry, there are some disadvantages. Among these, that there is no chemical information in these measurements, and it doesn't work well with thick layers, and it is relatively slow. These are well-known problems, and people have addressed these before. There are a number of references given on the slides, which you can look up. And particularly infrared spectroscopy together with neutron reflectometry has been implemented before. There was a beamline in Berlin, the BioRef beamline, which my collaborator Rainer Dahint was involved in, and also some attempts to do ellipsometry together with reflectometry before. We decided we want to do these three methods together, and well, it is popular these days to put different methods together to increase the amount of information, the types of data you get during the same measurement. And in this case, it is, I would say, fairly straightforward. So when we set out to do this, we had some requirements. We wanted the setup to be modular. So each of these methods should be possible to use independently of the others. And that is, well, the reason why this is fairly straightforward is that you can access the sample interface, the solid liquid interface, from different directions with each of these methods. So there is actually rather little physical interference. So in the figure, we have infrared light coming from one side, we have the ellipsometry probing from the other side, and there will be neutrons coming perpendicular to the image plane here. And the modularity is related to the flexibility. We wanted this to be a setup that could be used at different beamlines, so it should be relatively easy to rearrange. And we wanted this to be portable. We found that we were using experiments at different beamlines, and we did not really want to be stuck with one facility or one beamline for experiments, but rather have the flexibility to do this at different places. Right. So doing this, we went for the simple solution using available optical components, off-the-shelf components, because this will save time and it will surely save money also. So the ellipsometry part of this setup is well, it's called the in situ ellipsometer from John Woolam. It is actually a setup that is designed for being built into existing systems, just the way we want to do it. And it is fairly compact, very fast, and this is a relatively new system also, so it really comes with modern technology. The infrared part is currently solved with a stripped down benchtop spectrometer. So the Thermo Scientific IG50 is basically an OEM version of one of their top line benchtop systems, which it is not ideally suited for the purpose it will turn out, but we will address this later. But these are the bits and pieces that we put together together with a liquid cell and some optical interfacing to do experiments with these. Now, images of these types of systems are hopeless because they will be very cluttered, because there's a flurry of cables and pipes and tubings and all sorts of things. But here's an attempt to show what the setup looks like. So at the center, there is the trapezoidal prism, the silicon block, which is actually the sample. Beneath is a liquid flow cell, and this liquid flow cell has optical ports for the ellipsometric system. So in and out at about 60 degrees angle of incidence angle. And from above, we have infrared light probing in a 3 reflection setup on this trapezoidal prism, and it's exiting on the top side also. This whole system, the setup with the ellipsometry part is included. Well, there is the neutrons coming. We were looking pretty much down the beam direction. This is included in the infrared setup, where it's more or less confined between 2 big boxes, the source and interferometer box and the detector box. And looking at it from above, we have the part that I was showing in the previous picture in the center. As I said, it's a little bit difficult to show in a simple manner what it looks like, partly because it's confined and because there's a lot of stuff around it. But this was set up at Figaro. We had a setup at D17 also. So one is horizontal and one is a vertical reflectometer. So the setups will be slightly different, but that was part of the idea, that it should be flexible and possible to use at different beam lines. So we have tested this setup with different systems. So Rainer Dahint has been working on a set of bilayer stacks, which I will not talk about today because of time issues. We have used a type of polymer system that we are interested in for anti-fouling purposes as a model system. So this is a copolymer, polyampholytic copolymer, or pseudo-ionic copolymer from cationic and anionic monomers. The data I will show will not be from copolymerized system, but just the homopolymers. And the geometry of the sample is this. We have a silicon block, an oxide layer, silane layer to couple the polymer to the oxide, and then the polymer. And this will be measured in a lower high pH. And things we are interested in is like, what is the structure of the hydrated layer, the polymer layer, because the structure of the polymer layer will determine its anti-fouling properties. How fast does it relax? What is the speed of change, the rate of change if you change the environment? What is the degree of ionization in the film, for example? And these are questions that will be answered by different parts of this combined setup. So we've done fitting of the reflectometry data. We measured the cationic and anionic polymers in different contrasts, D2O, CM3, H2O, and also under dry conditions. So each sample was measured in 3 contrasts at low and high pH. The reflectometry model is fairly standard, I would say, for this type of systems. Now here, ideally, we would like to fit the neutron and ellipsometry parts together. But there is an inherent difficulty here, because we are using these 2 different methods because they are good and effective in different ranges, in different thickness ranges, basically. And this should really be taken into account. Basically the data should be weighed differently in different on different length scales. So this is a non-trivial problem which we haven't really solved yet. I'll show an example of what you can get from the fitting. So from the reflectometry data, we obtain volume fraction profiles under dry, stretched, and collapsed conditions. Here we use the thicknesses obtained from this fitting as input to the ellipsometry model, and then calculating the optical properties we obtain from the ellipsometry model with this data. And the optical properties, well, we are using a Cauchy layer with 2 parameters, where A is the refractive index, basically. And if we look at the A values that we get sensible A values for the polymer. In some cases, these are under wet conditions, but not under dry conditions. And clearly,
2 more minutes.
Yes, thank you. If you look at the fits, you see that it doesn't really fit the data very well. So, well, to cut a long story short, we not yet know how to do this fitting, but this is something we're working on. We were doing infrared spectroscopy in parallel, and the data shows we can probe the bulk properties of the solution, so we can actually follow the contrast changes very accurately. And for this particular system, we were interested in following the protonation and deprotonation, and this we can surely do. It's worth noting that the layers here are quite thin for an ATR experiment. So in view of this, I'm quite happy with the quality of the data we get. So there's some extra noise because we come near the silicon cutoff here. But otherwise, this is working fairly well. So to summarize, we tested this complete system on 2 different reflectometers, and it works well so far. So performance is meeting our expectations, but we are not happy, and well, we're not resting. So we are still working to improve things. So there will be an upgrade of the infrared system, which will be on a separate slide to make it a little bit more flexible. We are adapting this setup for the ESS beamlines, and the intention is to have something that will be easy to use and useful for coming users. That includes also design for a sample changer, which probably will not be very easy to use with the infrared part, but certainly for the ellipsometry, I expect this to be working relatively well. And we are working on fitting the neutron and ellipsometry data. So the upgrade of the iris system is really a pressing issue to make this more easy to handle and make it more compact. So we will use a much smaller interferometer. There are a number of technical issues involved in the design here that I would be happy to talk with anyone who is interested, but it's not trivial to do this. But this will give us a much more compact and much more flexible system, and the whole setup can be pre-aligned, offline, and then just put into the neutron beam when you do the experiment. Yes, so that was it. I want to note that we've been working on this as a team with people from Linköping, Rainer de Hint and his 2 students from Heidelberg, and also Philip Gutfreund. This was funded by the Swedish Research Council. We got ample beam time from ILL through a long-term proposal, and adaptation for the ESS beamlines is supported from the ESS. And yes, thank you for paying attention.
Ms. Gausko, please. Something? We don't hear anything. We do see.
Okay, do you hear me now?
Sorry, now it's okay, fine.
I lost the unmute.
Okay.
So you can see my
ahead.
slide properly, right?
Yeah, sure.
Okay. Yes, so thank you for the introduction. Yes, today I would like to talk about my PhD project, which is resonant neutron reflectometry for hydrogen detection in thin films. Before starting, I just want to acknowledge my collaborators and my supervisors at the Max Planck Institute, of course, and at the MLZ, and also the collaborators in Jülich Center and from the Helmut Zentrum Berlin, which participated in the experiments. And I would also like to mention that some overlapping parts to our work can be found in this recently published paper. So before getting to the method, I would like to talk about motivation for this work. So of course, why are we interested in studying hydrogen in materials in general? And the most obvious answer to this is, of course, the field of green energy and environmental topic, where hydrogen is seen as a particularly important player, especially in the automotive field, where it could be used, for example, to substitute fossil fuels as for cars. However, in order to implement such technology, we still have a few targets that needs to be met, and in particular, on the storage of hydrogen gas, there still needs to be some improvement. So there is a huge research on finding new materials that are able to absorb and release controllably big amounts of hydrogen. Another branch where hydrogen has become more and more important is the field of physics where hydrogen is used as a dopant to modify electronic properties of a host material. So here are just few examples, some pretty recent ones. For example, here it has been shown a colossal resistive switch of rare earth nickelates when applying hydrogen atmosphere or oxygen atmosphere. Or in this case, it has been shown that there is a sensitive increase of superconducting temperature in iron-based superconductors via proton intercalation, or as well, hydrogen, it is used already in ionic devices. For example, in this case, due to its ability to change the magnetic anisotropy of a thin magnetic layer. So also in all of these cases, we are interested in knowing how much hydrogen is involved in the process and how much the quantity is related to the change of the electronic property. So of course, there are several methods that can be used to detect hydrogen in thin films. The most used are electrical resistivity, X-ray scattering methods, NMR, nuclear methods, and of course, neutron methods. However, so our ideal method of detection would be quantitative and direct in the sense that we do not need other calibrations to get the exact amount of hydrogen present. And so, for example, as this is the case of resistivity and X-ray methods. But also we would like to be able to study in situ absorption and desorption processes. And this is not possible with the high energy ions used in nuclear methods. So basically we are left with neutron methods, and in particular, since we talk thin films, with neutron reflectometry. So since NR has been very well introduced yesterday and today in several occasions, I will not spend time to explain details, but I'll just focus on its role with hydrogen. So because we are using neutron as a probe, of course, due to the strongly negative scattering lengths of hydrogen, we are very sensitive to this atom. And in general, this hydrogen in a film will decrease its scattering length density, as you can see here, before and after hydrogen absorption. And also, because neutrons are very weakly interacting with matter, it is possible to perform in situ measurement in hydrogen atmosphere. So even though neutron reflectometry is a very powerful technique, as it also been said in the previous talk, it cannot exactly be defined as a fast technique. So we need some time to measure the curve. So this is not ideal for measuring fast kinetics. So the idea of this project was to implement a conventional NR with a resonant neutron reflectometry. So what do we mean by resonant? The idea is not new. It was first introduced by Ignatovic and Radu, and that is to have a resonant enhancement of the neutron wave density at the depth of the host material. In principle, the principle is similar to that of a particle in a box with finite walls that we all know from quantum mechanics. So we have a particle, which in our case is the neutron, which interacts with a potential that in our case is the scattering potential formed by our layers. Now, if this potential has the shape of a well, as here in that example, the neutron gets somehow trapped in it and forms a standing wave as a solution of the Schrödinger equation. So in order to get this resonant enhancement, the only requirement is that our scattering length density depth profile has a shape of a well, and that means that we must sandwich our layer of interest between a substrate and possibly a capping layer with a big contrast in scattering length density. And moreover, we also must have a channel which is proportional to the neutron density that allows us to detect this resonance, and this can be spin flip scattering, secondary particles such as gamma and alpha, incoherent scattering, or even transmission. So now let's see the case of our resonator. So our design of the sample. We have chosen as a layer of interest niobium, which is a material with an intermediate SLD, and it's a well-known nitrogen absorber. So in order to obtain the resonant enhancement, we have chosen as a substrate sapphire, and we capped it with a platinum layer, which both have a higher SLD, as you can see here in the SLD versus depth profile. And you can see here in the last panel, this is the calculated neutron density versus momentum transfer and depth, and you can see here the resonant enhancement, thanks to the well present here. Now, if we consider a hydrogen absorption into niobium, this will decrease the SLD of niobium, and this will make the well more deep, and this results in a shift in the Q, so in momentum transfer of the resonance. And so this shift of Q is proportional to the hydrogen concentration through this formula. And this is pretty powerful because by following this resonance, this means that we can directly know the hydrogen content in the film. Just one comment, this formula is valid only when we neglect thickness differences or inhomogeneous absorptions. So it's we need to take into account when we know that swelling of the film is present, we need to take into account and put it inside to have a proper hydrogen content. So in order to have a proof of principle of the method, of course, we have done experiments. And first of all, we have measured full reflectivity curves at the beginning and at the end of the absorption process, which allowed us to retrieve the SLD profile before and after absorption. And what you see here in yellow and green is the spin flip intensity, where we observe this very strong peak, which is our resonance. As I said, I forgot to mention, in between our niobium layer, we had this thin cobalt, which is there just to have a non-collinear magnetization, which we use as a secondary channel to detect this resonance.
2 more minutes.
So, yes, and you can see here a zoom of this resonance peak and the pristine sample, and at the end of the absorption, there is this shift in Q as expected. So, however, each of these curves took up hours, and while in reality, the kinetics of absorption is pretty fast, in the order of a few minutes. So in order to do this, to see that kinetics of absorption, I employed RNR resonant neutron reflectometry. And we have done so with two modes. The first mode is a Q-scan, where we just follow our resonance with time. So we just scan a very small Q range, and this allows to decrease the measurement time. And knowing the shift, we can retrieve the hydrogen content, as you can see here. And the second mode was that of staying at a fixed Q in the resonance peak and just waiting there. And while the peak is shifting, we detected a change in intensity at this fixed position. And then hydrogen content can as well be retrieved. And here, simultaneously with RNR, we have also performed the in situ resistivity measurement, which is a well-known studied method for kinetics. And you can see in black is the resistivity. It fits pretty well with the neutron data, shows the same kind of kinetics. So what I want to mention is that if you see here, we were able to detect around 1% of hydrogen with a step of 10 seconds, which would be basically impossible if we employed only conventional NR. So, of course, there are some drawbacks, which is that we need to perform also conventional NR, nevertheless, to calibrate thickness changes or inhomogeneity in the sample, which is very important. But this method allows to have a very good sensitivity and allows to study very fast kinetics in various materials. All we need is a contrast between the material of interest and the substrate, SLD contrast. So this was our method. I will not repeat again. I just want to say goodbye with a picture of our instrument and Yuri, my mentor, and I want to thank you for your attention.